There we go. So this week we are welcoming Charles Efferson from the University of Lausanne to talk to us about arbitrary cooperation. So over to you, Charles.
Yeah, so thank you for inviting me. And thank you for joining. Today, I'd like to talk about repeated play of social dilemmas. So it's a relatively new topic for me, and most of what I'll show you today is a project I'm squarely in the middle of. So comments are welcome. I think it's fair to say that repeated interactions um, enjoy a favorable status among population biologists and among human evolutionary ecologists in particular, even to the extent that maybe paradoxically, repeat there's this sort of influential idea that we can and even probably should use repeated interactions as an evolutionary explanation for anonymous one-shot cooperation. So Hagen and Hammerstein proposed this idea long ago. For example, this is a nice quote summarizing the idea. Players might be cooperating in one-shot interaction with strangers because, for example, they're using a psychological machinery that evolved for reciprocal altruism, where cooperating in the first round is often a good strategy. Psychological machinery is wrongly activated, they mean in an anonymous one-shot case, but once activated, it functions as designed. And I think this idea seems especially compelling because it provides, if you're trying to come up with an evolutionary explanation for anonymous one-shot cooperation in humans, for example, it offers a workaround of some form of group selection, cultural or otherwise. And of course, many people find that desirable. So another quote here. We disagree, however, that results to date provide convincing evidence that genuine care for others is a group selected utility or norm. Our disagreement stems from the fact that little is currently known about the frames players are using to interpret the experimental economics game cited in support of group selected strong reciprocity. So the logic behind this argument is, or the intuition even is straightforward. So imagine you're an ancestral hunter-gatherer in the late Pleistocene, and you're sort of walking through the forest, and you meet someone for the first time. And ex ante, you don't know, is this going to be a one-shot interaction or a long-term relationship? But you have to commit once and forever before anything happens to either playing, unconditional defection indefinitely or tit for tat. And in this setting, there are basically two key errors you can make. So one error is that you could choose to play tit for tat and what turns out to be a one-shot interaction when you're paired with someone who's defecting. Okay, so this is a relatively cheap error that costs you pay a one-time cost of C, let's say. Very different error is you can choose to defect in what turns out to be a long-term relationship when you've been paired with someone playing tit for tat. And that can be a very expensive error. In particular, as the continuation probability, delta here, approaches one, then that error goes to infinity, basically. So the idea is that uncertainty about whether it's a one-shot interaction or a long-term relationship creates a situation where selection favors risking the cheap error in order to avoid the expensive error. And in cases where, so you sort of preemptively choose tit for tat, basically. And in cases that turn out to be a one-shot interaction, that manifests itself as something that looks like one-shot cooperation. What's really going on is tit for tat is the risk dominant equilibrium of the super game, basically. Okay. So early experimental evidence seemed to sort of support this idea. For example, players were more pro-social in a one-shot anonymous game when they were in the sort of presence, when the environment had some kind of payoff irrelevant reputational stimuli, something like these eye spots here, compared to a control. And early models also seem to support the logic of the argument. Okay. However, so the idea here is, yes, we have this evolved psychology that's a reputation-based psychology that's hypersensitive to any indication that our reputations might be at stake. So even the slightest stimuli of that sort, and we slip into reciprocity mode, basically. Okay. The problem with that is that these experimental eye spot results, they've attracted a lot of attention, but they don't replicate very well. And if you take the model like the one I just suggested and you extend it, in particular, you extend the strategy space in some way that allows people to recover from an initial mistake and defection, then the models behave completely differently. So the scenario I just described to you, because you have to commit to defection or tit for tat before anything happens, you can't change once you get to interaction, the second interaction, for example. Once you know it's not a one-shot interaction, you can't revise your strategy in any way, or strategies that allow you to respond to that information are not allowed. That's what generates the cost asymmetry that drives the result. But as soon as you expand the strategy space to allow a richer set of possibilities, you basically attenuate the cost asymmetry a lot, and you do not get this sort of preemptive cooperation on the first interaction. It doesn't evolve. Okay. So several people have made that point. Today, however, I'd like to consider, I guess, what you might call a more fundamental point. And the idea is, well, let's get rid of the uncertainty altogether and just say interactions are repeated, period. Do repeated interactions actually support the evolution of cooperation in any reliable or meaningful way? Now, if we're talking about the repeated play of a kind of a standard prisoner's dilemma, by which I mean a game with a binary action space, as far as I know, the most comprehensive approach to this problem has been done by Matthijs and his co-authors. They have a couple of papers on this now. And they basically, correct me if you disagree with how I'm portraying this, Matthijs, but they basically allow an unrestricted strategy space, which in a game with a binary action space requires you. So you have to allow strategies that condition on increasingly long histories of play, basically. But when you do this, you get this phenomenon. We see an example in this upper part of the graph here, where cooperative strategies appear. They don't last very long. So they come, but then they go. And this happens over and over and over again with different mixes of strategies each time. Okay. Now, I'm a big fan of that work, but I also think a skeptic might object by saying, well, to extend the strategy in space in that way, you have to sort of posit players that have long, detailed, accurate memories where they can really condition on long sequences of past interactions. Some people might object to that. So last year, my co-authors and I, we published a paper where we worked with a game that has a continuous action space. And one consequence of that is if you're working with a continuous action space, you can examine effects associated with manipulating the strategy space without increasing the memory length. So in this case, we're going to limit attention to lag one strategies. You only condition on the most recent choice of your partner, but you can still manipulate the strategy space in various ways. Okay. So it's certainly true that games with binary action spaces have received a lot more attention in the evolutionary literature, but we're by no means the first one to look at continuous action spaces. There have been several games of that sort, going all the way back to an important paper, at least all the way back to an important paper by Roberts and Sherritt in Nature in 1998. But in any case, for our setting, we're working with a game. The stage game is a sequential game. Each player has an endowment of 1 for the stage game, can transfer any amount, and there are efficiency gains given by B in both directions. Okay, so here are the payoff functions for players 1 and 2. In this case, a strategy consists of an initial transfer, which is only relevant for the first mover in the first interaction, and then a lag 1 response function. So the response function is basically, it gives a focal player's current transfer as a function of the partner's most recent transfer. And in this paper that I'm going through briefly from last year, we systematically, we sort of manipulated how flexible we allowed these response functions to be. Okay. So in what we call the two-dimensional case, this is these two upper panels here, we allowed linear strategies above the 45-degree line. So you escalate the degree of cooperation under repeated play. And we allow linear strategies below the 45-degree line. So you de-escalate cooperation. And then, of course, we allowed the 45-degree line itself, which we call perfect reciprocity. That's it. So nothing else. In the three-dimensional strategy space, so we now extend the strategy space. And what I mean by that is we're working with a strict superset of strategies. And in this case, we just give each response function a left and a right intercept. So we allow any line in this space, which in particular means we now have response functions that can cross the 45-degree line. I'm going to call those ambiguous strategies. They'll come up a lot later. But importantly, ambiguous strategies are not allowed in the two-dimensional case. And then lastly, in the four-dimensional strategy space, we allow a wide array of nonlinear response functions. They can have this kind of sigmoidal shape. They can have something that's like an inverted sigmoid. All of that's possible. The only restriction is that any inflection point has to occur at 1/2 in this case. Okay? So we found in that earlier paper that cooperative strategies both invade and persist under a wide array of conditions. I'm only showing you a sample here, but this is representative of the larger set of results. They invade and persist when the strategy space is two-dimensional. So in particular, you're excluding these ambiguous strategies that cross the 45-degree line, but that's never true in the higher dimensional strategy spaces or the more flexible response functions. Okay. As a brief aside, I won't talk about this further, but just to wrap up this paper quickly, as a brief aside, we also found that when you're working with one of these higher dimensional spaces where repeated interactions by themselves do not support the evolution cooperation, in those cases, we saw strong positive interactions in terms of with respect to repeated interactions within groups and competitions between groups, so group selection, basically. And in those cases, the strategies that evolved consisted of high initial transfers and escalating reciprocity with in-group partners and low initial transfers and de-escalating reciprocity with out-group partners. And that sort of strategy profile is exactly what we observed in a one-shot anonymous game that we played with Parepkas and Nenekas in the highlands of Papua New Guinea. So blue here is in-group strategies and green is out-group strategies. Okay? So what were sort of the conclusions or summary claims that came out of that paper? I'm going to focus on one for the rest of the talk, but very quickly. The first one is that repeated interactions as a standalone mechanism do not reliably support the evolution of cooperation without arbitrary restrictions on the strategy space. However, when you're in the setting without the arbitrary restrictions, you get sort of strong positive interactions between competitions between groups and repeated interactions within groups. The result is escalating reciprocity within group members, de-escalating reciprocity without group members, which is what we saw in our behavioral experiment. Okay, today I'm going to look further into this claim that repeated interactions don't support the evolution of cooperation without arbitrary restrictions. And to do so, I'm going to, so I've now examined, quite recently, I've examined a total of 8 different strategy spaces now and 7 different approaches to implementation errors in all combinations. So we'll look at that in a minute. That's where we're headed, is all sort of what happens in all 56 combinations, basically. But before we do so, I want to go over some basic analytical results. Most of this is from the earlier paper, although I've changed how I'm presenting it here a bit. But the reason is these analytical results, let's say they've shaped my intuition about the design of the larger simulation project. So most of what I'll show you later are a lot of results from simulations, but the design of the project were shaped by these analytical results. Okay. And to show you that, I'm going to temporarily redefine cooperation, not in terms of what you give to your partner, but in terms of what you keep. I only do that because it makes the calculations a lot simpler. But a practical consequence of that is whether you're talking about initial transfers or the degree of escalation. I'm going to focus only on escalating strategies because that's where the problem arises. But in either case, it means that small numbers now mean more cooperation instead of big numbers. Okay, so I'll show that on a graph in a second. All right. And I'm going to be basically adopting an adaptive dynamics framework. So I'm going to be assuming a resident monomorphism and ecological steady state, basically, with a rare mutation that's nearby in the strategy space. Okay, so I'm limiting attention to local mutations, which is typical in this approach, and that's going to prove important down the road in various ways.
Excuse me.
Okay, yes.
You've got psi between 0 and 1
Mm-hmm.
in B. Is
Yeah,
that necessary? What's the meaning of that? That you retain
yeah,
less than they did? You can't retain more than they did, or
yeah. So this is the proportion of your partner's most recent transfer that you retain.
oh, okay,
So,
okay, sure.
so, so as I said, I'm
I get
limiting
you. Yeah,
attention
yeah.
now to escalating strategies. So
Okay.
if the value is 1, that means you match your partner's move measure for measure. If the value is 0, that means you retain nothing. So you just go straight to full cooperation.
Absolutely. So I was
Yeah,
thinking of psi t as a proportion, but it's not. It's the kind of absolute. Well, it's a proportion of a proportion.
exactly, exactly. Yeah, right. Yeah. It's the proportion of the endowment that your partner most recently transferred to you. Yeah. Okay. So in any case, if you adopt this approach, you can calculate the individual fitness values, the invasion fitness, and the selection gradient. In this case, to clarify, I'm focusing on the 2-dimensional strategy space for the moment. So that means I'm excluding ambiguous strategies where the response function crosses the 45-degree line. So if you do that, so I'm showing you now the space of possible escalating strategies. So this is the initial transfer. This is the degree of escalation. And to remind you, small numbers are cooperative. So this corner down here is your initial transfer is everything. You start by transferring everything and you escalate to the maximum degree immediately. Okay. This corner here is you start by transferring everything, but then your response function is the 45-degree line. So you always match what your partner did most recently perfectly. And then everything along this boundary are different degrees of escalation. Okay, so with those practicalities out of the way, what you'll see here is that the system converges on a point here on the boundary. This is not a singular strategy. You just hit the boundary in this case, characterized by maximum initial transfers and a specific degree of escalation. Okay, right here, this point here. I'm going to zoom in on the relevant region of the strategy space here just to see it better. Now, the problem here, and this is the vulnerability associated with these cooperative escalating strategies is that there's another curve in this space very close by. In this case, it's right here. And on the other side of that curve, the population is susceptible to invasion by these ambiguous strategies where the response function crosses the 45-degree line. Okay, so what that suggests is you only need a tiny amount of drift, which you will tend to have in a finite population, to end up on the other side of this curve, at which point the population is vulnerable to invasion by ambiguous strategies, and you can show that ambiguous strategies are in turn vulnerable to invasion by de-escalating strategies. So as soon as the ambiguous strategies start to move into the population, it's just the first step in the collapse of cooperation, basically. Okay, now in this case, you'll see that the continuation probability is 0.7, so pretty low. You expect about 3 interactions, more or less, on average. What happens if you increase the delta? So repeated interactions become more important. So here we're looking at 0.99, and you'll see that this region, this relevant region of space, everything gets really close together. If you look at the axis here, right, they're very small differences. And this other curve that gives you susceptibility to ambiguous strategies is extremely close by in this case. In fact, you can show that as delta approaches 1, these two curves converge, basically. So in that sense, the more important repeated interactions become, the greater this susceptibility or fragility I'm discussing, the more important that becomes too. You only need a very tiny amount of drift to enter the critical region of the strategy space. Okay, so what does this mean? It's something like this. Here's a simple graphical depiction. Imagine the population converges on some degree of escalation, like this green line here. Well, there's another degree of escalation very close by. If the population ends up there, then it's susceptible to invasion by another nearby ambiguous strategy. Okay? And simulations, this is from the earlier paper, show exactly this pattern. So these are evolutionary dynamics from the two-dimensional case when ambiguous strategies are not allowed. So what I'm showing you here is 50 independent simulations. I know it's a lot of lines here, but you'll see they all converge to some degree of escalation, and then that stays in place, basically. Okay, when you move to the three-dimensional strategy space, so now you allow ambiguous strategies, everything looks completely different. So this is the left intercept of the response function and the right intercept. You'll see escalating strategies evolving, but around about that time, the right intercept starts to collapse, and that's the collapse of cooperative strategies more broadly, because this is leading to de-escalating strategies, which of course, under repeated interactions, de-escalating strategies lead a pair to converge to zero cooperation. Okay. Now, very quickly, before I turn to the new work, a sort of corollary of this is if you had some mechanism that led the population to converge to a different degree of escalation that's relatively far away from this susceptibility boundary, or whatever you'd like to call it, then you don't necessarily have a problem, even if you allow ambiguous strategies. Because if the ambiguous strategies appear, they're appearing in a region of the strategy space where the population is not susceptible to invasion by these strategies. Okay, so why would this happen? It can happen for a couple of different reasons. We'll look at both possibilities. It could happen because of how you define strategies. Something like this may occur, and it can happen because of a particular type of implementation error might also do something like this. And we'll look at both. Okay. In any case, if something like that happens, ambiguous strategies don't represent the same threat that I mentioned or explained a few minutes ago. Okay. So what are the sort of summary intuitions that come out of this that I use to sort of guide the design of the larger project I'll show you in a second? So the first is to simply say, well, some strategy spaces preclude ambiguous strategies altogether. And of course, that protects the population completely from invasion by ambiguous strategies. I think more subtly, it's also possible in various ways to have a situation where you allow ambiguous strategies, but the population converges to a region of strategy space where ambiguous strategies either don't represent a threat or they're very far away in the strategy space. So local mutations will not get you there. Both of these things are possible. In either case, ambiguous strategies are possible, but they're sort of, let's say, statistically speaking, they don't represent much of a threat to cooperative strategies. Okay, and we'll look at examples of both of those. But I think the general question is, in all cases, we have to ask ourselves, are these outcomes artifacts of arbitrary restrictions on the strategy space?
Right.
Okay.
So, sorry to interrupt. Just so you're going to
Mm-hmm.
be looking at things to inhibit drift towards these invadable regions.
Exactly. Some of the mechanisms I will show you will have that effect. Yes.
Okay.
Yeah. So I think maybe the best way to do this is I'm going to sort of rip through the 8 strategy spaces and then rip through the 7 approaches to implementation errors, just to sort of show you the structure of this. Of course, you can always stop and ask questions. But it's possible that the logic of some of the choices won't be immediately obvious. But I'm going to then show you summary results, and I'm going to loop back around and focus on some specific results. And I think that will hopefully at that point, some of the choices in the overall design, the reason for it, for those choices will come clearer at that point. Okay. So let's start with the strategy spaces. So the first one is the two-dimensional space from the paper last year, which was actually first proposed by Lee and Boyd in 2007. So just to remind you, this allows linear response functions above the 45-degree line, linear functions below the 45-degree line, and the 45-degree line itself. Okay. I'm going to use, in all cases, I'm going to give you these little mnemonic devices to help us remember what we're looking at, because I'm going to show you all 56 combinations on a single graph later. And if I just call this strategy space A, I don't guess no one would remember what that means. So maybe try to remember these mnemonic devices. But this is the one I use to represent the two-dimensional strategy space. Okay. Next is the three-dimensional strategy space from the earlier paper. This simply adds the possibility of these ambiguous strategies that cross the 45-degree line. And that's the mnemonic device there. Another approach to a three-dimensional strategy space was first proposed by Val and Novak in 1999. And in this case, the response functions are simply any line in the two-dimensional plane. And if that line intersects the unit square somewhere, like here, then you see it. You actually see the line. But anywhere it's outside the square, you just clip the behavior at the boundary. So if the line is above 1, you simply transfer 1. If the line is below 0, you simply transfer 0. So response functions in this case are piecewise linear, but once you hit one of the boundaries of the action space, you stay there. You can't get away from the boundary. Okay, at that point. And here's the mnemonic device for that. The next strategy space is a four-dimensional space. And this is exactly like our three-dimensional space, but I'm adding a discontinuity at the left boundary. So what that means is what you do if your partner transfers 0 does not necessarily have to be the same thing as what you do as you consider the limit of this response function as you approach here. Okay. Here's the mnemonic for that. This is the 4-dimensional space from the earlier paper. Again, it allows these nonlinear response functions. They can be sigmoidal shaped, inverted sigmoid. Any inflection point has to be at 1/2 though. Next is a 4-dimensional strategy space, which is the response functions are the same as our 3-dimensional space, but I've now introduced a trigger. I'd like to thank sort of Ed Seabright and co-authors for pointing out this possibility to me, but it's basically an evolutionary version of Grimm trigger. So the way this works is if you start off with your trigger inactive, of course, but if at some point your most recent move is too large compared to your partner's most recent move, then the trigger becomes active. And from that point on, you simply defect for the duration of the relationship. You defect completely. And the threshold that activates the trigger is the 4th dimension of the space. So it's a heritable trait under selection. Here's the mnemonic there. This is my attempt to draw a trigger. And then the next is a 5-dimensional space that allows nonlinear response functions. So this is simply a generalization of the nonlinear 4-dimensional space I showed you a moment ago. The only difference is now the inflection point can be anywhere. So again, functions can be sigmoidal shape, inverted sigmoid, but the inflection point can be anywhere between 0 and 1. Okay? And then lastly, this is a generalization of the Val and Novak strategy space in the sense that I'm working now with piecewise linear response functions, but I allow any piecewise linear function. So in particular, once you hit the boundary, you're not stuck there. You can get away from the boundary again. Okay? Now, here are the set relations between these 8 strategy spaces. And what I'd like to point out in particular, so these are the 3 strategy spaces we worked with in the previous paper. All of them have been generalized in one or more ways in the precise sense that I've now added strategy spaces that are strict supersets. Okay, so we're never removing anything. We're always adding strategies to the set of possible strategies that can appear via mutations. Okay. Any questions on that before we go to the errors? Okay. So now I turn to the 7 approaches to implementation errors. So the first is no errors at all. That simply means that whatever your strategy tells you to do, that's exactly what you do. The next are local errors. And I think this is quite realistic if you're talking about a continuous action space. I mean, what's the probability that you do exactly what your strategy says in that case? But basically what it means is if your strategy specifies a given transfer, actual transfers are now distributed locally around that according to a truncated normal distribution. Okay. So again, I'm also using mnemonic devices for the errors here. This is the mnemonic for local errors. And then next, the remaining 5 types of error are different ways of modeling errors as simply defection, where you transfer 0. And the reason for that, I think, is because several authors have argued convincingly, Sheridan Roberts in particular, that you need mechanisms in a system like this that maintain defection in some way. And the reason for this is that if you don't have that, the disciplinary function of reciprocal strategies never becomes manifest. And this, of course, in turn allows strategies that cooperate but don't discipline to drift in and eventually render the population vulnerable to invasion by less cooperative types somehow. So McNamara and Limar have this nice quote: costly defenses against exploitation cannot be selected for and maintained if exploitation never occurs. But if errors are take the form of defection, well, there are actually many different ways of doing that, and that's what somehow the five remaining error structures are going to be.
So
Matthijs?
can I ask you a question? So you say you mean that this is convincing in the sense that as a way to keep the reciprocity alive in the process, but you're not saying that this is a convincing way that errors or this is a convincing way that they mimic how errors in reality would be,
Yeah,
or is it?
exactly. Exactly. I'm not making any claim about how realistic these errors are, although some of them seem okay to me. You'll see the details in a second. Your interpretation is correct. I'm saying it strikes me as a good argument for a mechanism that you need to help maintain reciprocal strategies. If you don't have it, you have this problem with, strategies that cooperate but don't discipline drifting in. Okay. So the first approach to this, the idea here, it's like a trigger. It's like grim trigger, but it's not strategic. It's an error. So the idea here is you start off in the non-error state, but every interaction, the error probability applies. And if you switch into the error state, you never go back. So once you're in it, you just defect for the duration of the relationship. So errors are a one-way movement from the state in which you don't commit the error to defection for the rest of the relationship. Okay. At the opposite extreme is you're in the non-error state. You switch into the error state with some probability. If you're in that state, you defect, but then you go back immediately into the non-error state and you apply the error probability again. Okay. So you can imagine, of course, intermediate probabilities of going back. I haven't considered that. I've just considered these two extremes where you never go back or you go back immediately with certainty. But in this case, when you have this two-way movement, you go back immediately. The upshot of that, of course, is that errors are then IID at the interaction level. So you're flipping a coin for each interaction to see if you commit the error. Here's the mnemonic for that. The next possibility is I couple the one-way errors with local errors. So the idea is if you commit the defection error, then you just transfer 0. But conditional on not committing that error, then you have local errors. The reason I added the local errors, by the way, is I had this notion that all else equal, local errors would increase the importance of drift, right? Because they sort of decouple what people actually do to some extent from what their heritable strategies are telling them to do. I haven't found much evidence that that's the case yet. Maybe if I made the variance of the error distribution really big, it would be different. But so far, I haven't seen that. Anyway, that was the logic there. And then lastly, or next, is the two-way approach to errors as defection. And then again, conditional on defection not occurring due to an error, then errors are local. So they're just locally distributed around what the strategy says. All right, and then the last type of error I just call all D. And the idea here is you apply the error probability to the entire relationship. So let's say I meet Matthijs for the first time. If I commit the error, I start defecting immediately and I defect for the entire duration of the relationship. That's it. If I don't, then I never commit the error and I simply do what my strategy tells me as we continue to interact. Okay. All right. So I manipulate a lot of things that I won't go into here in terms of the migration rates between groups and all sorts of initial conditions, life cycles, et cetera. I think in the interest of time, I'm just going to tell you, we can talk about this if people are interested, but I'm going to, for the most part, focus on conditions that are most conducive to the evolution of cooperation. because you're going to see that the problems are significant there. If we were to look at other cases, the problems would be even worse, basically. That's the idea. Okay? And just to clarify, I'm now working with situations in which pairs interact 100 times. Okay? So strategies are only backward looking, so I just fix the number of interactions they have. Okay. The one exception where I'm not going to focus on the most favorable case is here. And this is based on what I think of as ancestral initial conditions. So I'm seeding all populations initially with agents who are perfectly selfish, okay, which is presumably the ancestral condition for the evolution cooperation. And you'll see the full space of 56 combinations here. These are the strategy spaces and the different types of error. And what I'm showing you here is the mean transfer. So I'm averaging over 30 independently simulated populations. So that's what we see here. The mean transfer is a function of time with 99% confidence intervals. That's the gray stuff here. And what you'll see is in the two-dimensional case.
You say that again so that I understand?
Yeah, so this is the mean transfer. So every agent is paired with someone and transfers something over the course of their relationship. And you can average over all those values for a given generation. So that's what we're looking for. And I'm averaging over multiple populations actually too. Okay. And the confidence intervals are clustered at the population level if you're interested in that. But anyway, the upshot here is you'll see that in the two-dimensional case, so as these values go up, the population is becoming more cooperative, essentially. You'll see here that cooperative strategies start to move into the population, although it's a very slow process, let's say. This is over the course of 150,000 generations. You'll see something loosely similar to that, although it's weaker under the trigger strategy here. And you'll see that this all D type of error also seems to lead to, under a variety of strategy spaces, tends to lead to some slow tendency for cooperative strategies to move in. Okay, so that pattern is going to carry over to some extent when we switch to different initial conditions. So here we're starting with maximally cooperative initial conditions. And you'll see something analogous in the following sense. So you'll see that the two-dimensional strategy space tends to, so cooperation is quite stable in that case. So we already knew that from the earlier paper. We'll see that the three-dimensional strategy space, if you don't have any errors, cooperation collapses. We also knew that. And we'll see here that with the trigger strategy, we'll look at this more in a few minutes, but we'll see cooperation drops quickly, but then it seems to sort of stabilize at around 1/3 or something like that for some error structures, not all of them. Okay, we'll look at that in a minute. And then you'll also see that all D errors, so this is where the entire relationship is characterized by the mistake. In some cases, this type of error stabilizes cooperation. You see here in the three-dimensional strategy space, when cooperation would not otherwise be stable without the error. Okay, if you look here versus here, for example. All right, so let's look at some specific results and try to sort of figure out why that's the case. But I'm going to start somewhere different altogether first. So let's first compare this restricted piecewise linear strategy space. This is the one proposed by Val and Novak long ago, to the more general piecewise linear strategy space. So you'll see here cooperation does decline, although it's a very slow process. Whereas under the more general strategy space, it declines, it collapses almost immediately and never recovers. So why would that be the case? if you look at the more restrictive case, you'll see in particular that in many populations, the slope of the response function is moving upward. Not always, but in many cases. So I'll show you in a second what I think that means. But in the more general case, with a general piecewise linear function, you'll see the sort of standard pattern. This is the left and right intercept. This is escalating strategies invading, but then the right intercept starts to collapse. And in particular, down here, we see the vertical component of this point in the middle where the kink is. And you'll see that goes sort of hard to zero and stays there, basically. So what's the difference between these cases? I think in the more restrictive case, where once you hit the boundary, you're stuck there, the strategies don't allow a general piecewise linear. I think what's happening is that the population is evolving towards some escalating strategy that looks sort of like this, okay? Now, ambiguous strategies are allowed under this strategy space, but they're very far away, okay? And because you're only allowing local mutations in the strategy space, they're effectively irrelevant because they only appear extremely rarely. So the vulnerability to invasion by ambiguous strategies is sort of, it's not very important because those strategies are just too far away. And this is a function of how the strategies are defined in this case. But if you have the more general approach to piecewise linear response functions, then an ambiguous strategy is a very, very close by, right? That's just a local mutation from here to here. And that's exactly when cooperation collapses, because in this case, you end up with response functions that look like this, which of course lead a pair very quickly to not cooperating at all. Okay. Now let's think about this all D error, which under various circumstances does seem to stabilize cooperation when cooperation otherwise would not persist. So if we look here versus here, for example. So why is that the case? So this is the scenario we've already looked at, the three-dimensional response, the strategy space with no error. And you see the standard pattern, escalating strategies evolving, but then the right intercept collapses and you end up with uncooperative population, okay? Here is what exactly the same, but we've simply added this error. And what I want you to notice is that the degree of escalation the population moves to is lower in this case. And that stabilizes cooperation in the long run. Now, why is this the case? Without the error, remember, this is what I explained earlier, the population converges to a degree of escalation that's extremely close to this boundary where it's susceptible to invasion by ambiguous strategies. Okay, that's what's happening in this first case. But think about the error. What happens if the error here? So Matthijs and I meet in the forest again in the late Pleistocene. And I commit the error. So I start defecting immediately and always defect. That means if Matthijs does not commit the error, then he will transfer the amount given by this left intercept over and over and over again as we continue to interact. So this left intercept is a kind of measure of the extent to which I will repeatedly exploit him by making this mistake. So that means when you introduce this type of error, it creates a countervailing selective force that pushes, it creates a trade-off essentially between escalating quickly when your partner does not make the error and limiting exploitation when your partner does make the error. That trade-off is resolved in the sense that the system converges to a much lower degree of escalation. So in this case, even if ambiguous strategies appear, which they do, they don't really matter because the population is in a region of strategy space where these ambiguous strategies don't represent a threat. Okay, so that's the difference between these two cases, basically. And you can see it if you look at the left intercept. It goes higher here than it does here. And that's exactly what's protecting cooperative strategies when you add this error. But
May I ask a question?
yes.
So your line where it becomes susceptible doesn't also change if you introduce all D? Or am I just not understanding this?
Yeah, so I don't know actually. So again, as I said, the analytical results I showed you were just to sort of cultivate intuition. I don't have any analytical results with this error in place that also considers this susceptibility boundary. But that's a good idea. I need to think about that. I'm assuming, perhaps incorrectly, that invasion curve doesn't move actually, and that could be wrong. Yeah. But I would point out that if you look at these three strategy spaces, okay, they offer you different ways of decoupling the left intercept of the response function from what happens over the rest of the function's domain. Okay, this is especially clear when you allow the discontinuity. What you do when your partner defects completely is unrelated to what, or doesn't need to be related to what happens over with the rest of the response function. So that attenuates this trade-off I mentioned. And if you don't like the discontinuity here, of course, these two approaches to defining the strategy space give you a continuous way to do that too. And you'll see that in all three of these cases, we recover the original result, that cooperation does not persist. So the strategies break down quickly and stay there. Okay. Now the last, you see that here, if you look at the spaces, so this is the discontinuity. You see the standard pattern, escalation evolving, right intercept starts to collapse. This is the nonlinear version. And actually what's happening here with all five of these dimensions is that strategy spaces, response functions are evolving to have exactly this kind of shape here. And once that happens, you see the right intercepts start to collapse. And then the general piecewise linear, these are the dynamics for that. This is the left intercept and the right intercept, which of course is collapsing. And then once again, we see the vertical component of this kink here, the point that gives you this kink, we see that vertical component going to zero quickly and staying there basically. In all cases, you end up by generalizing the strategy space with no long-run cooperation. Okay, and then the last thing I'd like to highlight is this trigger strategy. So I haven't worked out what I think is really going on here, why this is happening. I'm still thinking about this, but you'll see, if you just compare these 2 points, you'll see everything's the same here, except I've added the trigger relative to this scenario. You'll see it drops, but it doesn't go all the way to zero, and it sort of stays here at this intermediate level for a long time. Trigger strategy does very badly under certain error structures, but I'm going to focus on this case here. What's going on here? So what's not happening, it's not going to this intermediate level and staying there. What's happening is that the populations are actually cycling, and I'm showing you the average over multiple populations here, okay? So here I'm showing you the mean transfers for all 30 populations. I know this graph is not easy to look at, but if you pick out individual lines, you'll see sometimes they're sloping downwards, okay? So that's cooperation collapsing, but you'll also see lines sloping upwards. So that's cooperation sort of re-invading. So I need to show just a single population over very long term, and I guess it'll be easier to see the cycles. And then if you look at the strategy spaces, you see something similar. It's even harder to see here, but this is the right intercept the response function, and you'll see some populations going down, but you'll also see some populations going back up. So For some reason, I don't know why exactly adding the trigger does this. As I said, I don't have a clear idea about this, but simply adding the trigger to this space leads the population to cycle in this way. And when you average over multiple populations, you get this intermediate level of cooperation in the long run. All right. So that's basically where I'm at the moment. So just to quickly wrap up, I would say the following. Of the 56 combinations of strategy space and error structure examined here, given a combination that supports cooperation, there's typically some strict superset of strategies or alternative error structure that will destabilize cooperation. Okay. The one sort of partial exception that I'm still thinking about is the trigger space. But more generically, one way of thinking about this is, in general, we can specify a model that supports the evolution of cooperation under repeated interactions as a standalone mechanism. We can also specify a related, equally plausible model that does not. And so I don't know how other people think about this, but for me, the choice between these two is arbitrary. I don't see any clear biological basis for choosing one or the other. And that's what I mean by arbitrary cooperation. And of course, it doesn't fit very well with, one might say the privileged status that repeated interactions enjoys compared to something like group selection. I think for me, this suggests that repeated interactions is also a quite problematic explanation theoretically, at least when you consider it in isolation without other mechanisms in a mix. But as the final caveat, I would like to say, of course, that the fragility of cooperation I'm highlighting here is not a general result. There's no proof or anything like that here, obviously. It's more of an inductive argument based on trying to consider this very sort of large space of combinations. Okay, so that's it. Thank you very much.
Thank you very much. Try to do the clapping hand gesture. There we go.